Automation and control for electric motors and auxiliaries. Automation and control systems in electric motors and their auxiliaries play a crucial role in ensuring optimal performance, safety, and efficiency. Below is a comprehensive breakdown of how these systems handle inputs and outputs, I/O, trips, alarms, and continuous control. 1. Motor control systems. Implementation of automation and control, input-output, I/O, inputs, start and stop commands, motor load conditions, thermal feedback, and power quality signals, voltage current. Outputs, control signals to contactors, relays, speed controllers, and visual indicators, e.g. motor running lights. Trips, automatic trips are activated when predefined thresholds are exceeded, such as overcurrent or short circuit conditions, motor stall, locked rotor conditions, undervoltage or phase loss. The system cuts power to the motor and activates emergency braking where necessary. Alarms. Audible and visual alarms alert operators to issues such as abnormal vibration, high motor winding temperature, or loss of phase. Local human-machine interface, HMI, panels, or remote supervisory control and data acquisition SCADA systems provide detailed fault indications. Continuous control. For centralized control, multiple motors can be managed via programmable logic controllers, PLCs, or distributed control systems, DCS. Automatic adjustment of speed, torque, and load sharing is possible for process consistency. Speed control is typically achieved using variable frequency drives, VFDs, or thyristor-based controllers. 2. Protective instrumentation. Implementation of automation and control, input-output, I/O, inputs, current sensors, temperature sensors, and phase detectors send continuous feedback. Outputs, control signals to trip relays, cooling system fans, and breakers. Trips, protective relays initiate trips when winding temperatures rise above safe limits or a short circuit event occurs. Locked rotor protection detects if the rotor is not turning despite applied power and trips the motor to prevent overheating. Alarms. Alarms warn of minor overloads, phase imbalances, or cooling system faults before triggering a trip. Configurable alarm thresholds allow operators to respond to potential failures before they become critical. Continuous control. Overload protection uses real-time current measurements to regulate motor output within safe limits. Thermal overload relays adjust their response based on ambient conditions to avoid unnecessary shutdowns. Speed and torque control systems. Implementation of automation and control, input-output, I/O, inputs, speed set points, load measurements, and feedback from encoders or tachometers. Outputs, PWM, pulse width modulation, signals to VFDs or other motor drives. Trips, speed controllers initiate trips if the motor exceeds set speed limits or fails to maintain synchronous speed. Sudden drops in torque or overspeed events trigger system shutdowns. Alarms. Alarms indicate issues such as overspeed, underspeed, or torque inconsistencies. Motor health indicators on control panels show performance trends. Continuous control. Continuous monitoring and adjustment of speed based on load demand improve process performance. Automatic adjustment of torque ensures safe acceleration and deceleration. Closed-loop control systems maintain target speeds using proportional integral derivative, PID, algorithms. 4. Monitoring and feedback systems. Implementation of automation and control, input-output, I/O, inputs, sensor readings for temperature, vibration, bearing pressure, and oil flow. Outputs, alerts, shutdown commands, and reports to local displays or remote systems. Trips, triggered if bearing temperature exceeds safe limits or oil pressure drops critically low. Feedback sensors send real-time data, and the control system initiates shutdowns to prevent catastrophic failure. Alarms. Early warnings indicate trends such as gradual bearing wear or increased vibration. Alarm states are logged for maintenance planning and trend analysis. Continuous control. Systems continuously adjust lubrication flow rates or cooling fan speeds based on sensor inputs. Adaptive control ensures the motor remains within optimal performance parameters under varying loads. 5. Safety and environmental controls. Implementation of automation and control, input-output I/O, inputs, gas sensors, temperature probes, and pressure monitors in hazardous areas. Outputs, shutdown signals, airlock activations, and notifications to operators. Trips, Explosion-proof systems trip immediately upon detecting flammable gas levels or internal ignition to prevent escalation. Pressurized enclosures may activate emergency purging if internal pressure drops below a safe threshold. Alarms. Gas detection alarms, high-temperature warnings, and ventilation failure alerts ensure quick responses. Flame-proof motor enclosures include temperature monitoring with fault reporting. Continuous control. Pressurization control systems regulate inert gas or clean air within the enclosure. Continuous monitoring of air exchange ensures hazardous substances do not accumulate. 6. Advanced control systems for process integration. Implementation of automation and control, input-output, inputs, commands from distributed control systems or SCADA, process flow measurements, and operator set points. Outputs, motor speed adjustment, load balancing instructions, and control valve positions. Trips. Process controllers initiate trips when critical processes like conveyors or pumps fall out of synchrony with other equipment. Safety interlocks shut down systems during abnormal feedback, such as zero flow or blocked discharge. Alarms. Process alarms highlight discrepancies between expected and actual performance. Integration with plant-wide alert systems ensures that process deviations are quickly escalated. Continuous control. Advanced automation adjusts motor operation based on process feedback for maximum efficiency. Process optimization algorithms ensure minimal energy consumption while meeting operational demands. Automation and control in electric motors and auxiliaries involve a complex interplay of inputs, outputs, trip mechanisms, alarms, and continuous control loops. These systems work together to enhance reliability, safety, and process efficiency, enabling seamless integration into industrial operations.